All right, so today we are going to be diving deep into the world of reinforcement learning,
Reinforcement learning, yeah.
RL. We're going to be digging into Stanford's CS234 lectures
Yeah.
and basically uncovering how AI agents can learn not from like us giving them flashcards or whatever, but by actually doing stuff.
That's right.
So think like mastering a video game or even like figuring out a recipe through trial and error, except with algorithms and data.
Yeah, so like in a nutshell, imagine a robot
Okay.
learning to walk right. Instead of us having to program it
Right.
to, take a step here and then what happens if there's a bump in the road or whatever.
Yeah.
It can experiment and get feedback, maybe stumble a few times.
Right.
But eventually it learns to navigate that world on its own just through trial and error.
That's so cool.
Yeah.
Okay, so it's like how dogs learn tricks with treats,
Kind of, yeah.
but on a much more sophisticated level, I'm guessing.
Yeah, it's way more complex,
Okay.
dealing with really complicated problems. And we're talking about optimizing for long-term goals,
Okay.
not just immediate rewards.
Got it.
One lecture even calls this like a paradigm shift in AI
Okay.
that happened around 2015. And you can see why, like, think back to those DeepMind AIs
Oh, yeah.
that were playing Atari games like nobody's business.
They were so good.
Right. And that was RL in action.
Wow.
They were just following some pre-programmed rules.
Right.
They were learning and adapting.
So cool. Okay, so that's amazing.
Yeah.
But what makes RL different from other types of machine learning?
Okay, so imagine you're teaching someone to ride a bike. In traditional machine learning, it'd be like handing them a really detailed instruction manual,
Okay.
but never actually letting them on a bike.
Right.
RL is like throwing them right on,
Oh,
letting
yeah.
them figure it out.
Okay.
They're going to fall down a few times. They're going
Yeah.
to try different things,
Right.
but eventually they're going to be cruising down the street.
That makes a lot of sense.
Yeah.
It's like learning by doing.
Exactly.
But I'm guessing there are some challenges in actually teaching machines this way.
Oh, there are definitely challenges. One of the big ones is this thing called the credit assignment problem.
Okay, the credit assignment problem.
Yeah. So like, imagine you win a game of chess.
Okay.
Was it that one brilliant move you made at the beginning?
Right.
Or was it just a lucky break at the end?
Right.
Figuring out which actions actually led to that final outcome,
Yeah.
especially when the rewards are delayed.
Right.
That's a big hurdle in RL.
So how do they suggest we tackle that in the lectures?
So that's where it gets really interesting.
Okay.
They dive into a bunch of cool solutions.
Okay.
One is using what's called Monte Carlo methods.
Monte Carlo methods, what is that?
So it's kind of like running thousands of simulations
Oh, wow.
to figure out what the best strategy is.
So instead of looking at just one chess game,
Right.
you're simulating a million different games.
Exactly.
And seeing which moves lead to victory most often.
Yeah. So you get a really good understanding of what works best overall.
I can see how that would be computationally intense.
It can be, yeah.
Wow, okay.
And then there's this other approach called temporal difference learning,
Okay.
or TD learning for short.
Okay.
And that's more about learning on the fly.
Okay.
So instead of waiting for the whole game to finish,
Right.
you're adjusting your strategy every step of the way
Oh, that's interesting.
based on the feedback you get.
So it's like analyzing your chess moves during the game, not just after it's over?
Exactly.
Yeah.
You're constantly learning and adapting.
That seems a lot more efficient.
Right.
Wow.
And these techniques,
Yeah.
along with some others, they talk about,
Okay.
they help us tackle that credit assignment problem
Okay.
and let our RL agents actually learn from their experiences.
That's so cool. Now, you mentioned DeepMind using RL to kind of conquer those Atari games.
Yeah.
And the lectures talk about some really interesting algorithms, like deep Q learning,
Yeah.
which sounds super cool.
Deep Q learning was a big deal.
Yeah.
It combined the power of RL, that trial and error learning,
Oh,
with these things called deep neural networks,
okay.
which are basically these powerful pattern recognition machines.
So it's like giving them a brain.
Yeah, you could say that.
Yeah.
And that lets them tackle even more complex problems
Wow.
and learn much more intricate strategies.
That's incredible. But I'm guessing there's got to be a trade-off there, right?
Of course.
More power, more problems.
Yeah, you're catching on quick.
Okay.
Deep Q learning and those complex representations.
Yeah.
They're powerful, but they can be tough to work with.
Okay.
They need tons of data
Right.
and a lot of careful tuning to get them to learn effectively.
It's like a double-edged sword in a way.
Kind of, yeah. It's like anything else, right? You got to find that right balance
Right.
between complexity and efficiency.
Makes sense.
Sometimes a simple approach is going to be better.
Yeah.
Just like you don't need a supercomputer to balance your checkbook.
Totally. Okay, so we talked about those DeepMind AIs mastering Atari games.
Right.
But real-world problems are a whole different story, right?
Absolutely.
Like, the real world throws you curveballs you could never program for.
It's true. And one of the lectures actually makes this comparison
Okay.
between the complexity of like a chessboard
Okay.
and, say, teaching a robot to navigate a city.
Oh, wow, yeah.
Chess has a limited number of moves
Right.
and possibilities, but the real world, forget about it.
It's like infinite.
That's where we run into this thing called the curse of dimensionality.
Okay, the curse of dimensionality. Now that sounds intimidating.
It's a mouthful, right?
Yeah.
But it basically means as the number of possibilities explodes,
Right.
our traditional RL approaches, they start to struggle
Yeah.
because there's just too much to handle.
So how do we even begin to tackle those kinds of real-world problems?
That's where function approximation comes in.
Okay.
Remember we talked about representing complex information
Yeah.
in a more simplified way.
Right.
So instead of trying to account for every single possibility,
All right.
we can use techniques like linear models
Okay.
or deep neural networks to represent that huge space more efficiently.
So it's like using a map instead of trying to memorize every single landmark.
Exactly.
Yeah.
But and the lectures really highlight this.
Okay.
There are some potential downsides too. We have to watch out for what they call the deadly triad.
The deadly triad. Okay, what is that?
It's this dangerous combo of function approximation,
Right.
bootstrapping, and off-policy learning.
Okay, I gotta admit, you've got my attention with this deadly triad business.
Yeah, it's a bit ominous.
It does sound kind of ominous. What's the danger there?
So imagine you're trying to reach a destination,
Okay.
but the map you're using keeps changing
Yeah.
based on where you are and where you've been.
Right.
And sometimes it even throws in completely made-up places.
Oh, no.
You'd get lost pretty quickly, right?
Yeah, that's a recipe for disaster.
Exactly.
So how do we prevent our RL algorithms from falling into that trap?
Good question. The lectures actually give us some answers.
Okay, good.
One technique they talk about is called experience replay.
Experience replay.
Okay. It's kind of like reviewing game footage after a match.
Right.
The AI can learn from its wins and its losses
Okay.
and really solidify its understanding of what works and what doesn't.
That's cool. So it's like having this whole highlight reel of past experiences to learn from.
Exactly.
That's really neat.
Yeah.
Are there any other strategies they suggest?
Yeah, they also talk about these things called fixed cue targets.
Fixed cue targets. Okay.
Imagine trying to hit a moving target.
Okay.
If you're constantly adjusting your aim based on every little wobble,
Yeah.
you're going to overcorrect and miss right.
Right.
Fixed cue targets help stabilize the learning process
Okay.
by updating those target values less frequently.
So it's about finding that balance again, right?
Exactly.
Between reacting to new info and sticking with what you already know.
Right on.
Yeah.
And while these practical techniques are important,
Yeah.
the lectures also emphasize the importance of theory,
Right.
like understanding the Bellman equation,
Okay.
which describes the relationship between the value of a state and the values of its neighboring states.
So it's like understanding the underlying principles,
Exactly.
even if you don't need to know the equations by heart.
Precisely. And speaking of understanding the bigger picture,
Okay.
the lectures really dive deep into how we evaluate and improve an RL agent's policy.
What exactly does that mean? Like, how do you grade an AI?
It's a good way to think about it. So evaluating a policy is like looking at a student's grades
Okay.
to see how they've been doing.
Right.
But how do we actually help them improve?
Yeah, how do we get those grades up?
That's where algorithms like SARSA or Q-learning come into play.
No.
These algorithms are like study guides.
Okay.
They help the agent figure out which actions are going to lead to better grades or outcomes.
Got it.
But here's the thing, and the lectures really emphasize this.
Okay.
Simply being greedy, always choosing the action that seems best right now.
Right.
That's not always the best strategy.
Really? Why not? You'd think you'd always want to go for the best option, so it's like saying sometimes you got to take the scenic route even if it looks longer on the map.
Yeah, exactly.
Yeah.
Sometimes exploring those unknown paths,
Yeah, right.
it can lead you to something even better.
Okay, so how do we teach a machine that? Like, how do you program exploration?
Well, one interesting idea they talk about in the lectures
Okay.
is this concept called machine teaching.
Machine teaching. Okay, so are we teaching machines to teach themselves now?
In a way, yeah. So instead of just throwing tons of random data at an algorithm,
Right.
we could actually be more strategic
Okay.
about selecting which examples we show it.
So it's like we're curating the learning experience.
Exactly. And they give this cool example of teaching a machine
Okay.
to tell the difference between positive and negative numbers
Okay.
on a number line.
Right.
If you were going to do that with flashcards,
Yeah.
you'd need like a zillion examples.
Okay. That sounds super tedious.
Right. But with machine teaching, you might just show it one positive number
Okay.
and one negative number
Okay.
and let it kind of figure out the pattern from there.
So it's like giving it the key to unlock the rest of the information.
Exactly. It's about working smarter, not harder.
I like it. Now, one lecturer mentioned that even tiny details in these RL algorithms can have a huge impact.
Oh, yeah, they were talking about the discount factor,
Okay, the discount factor.
or gamma, as they call it.
Okay.
And it basically determines how much weight the agent gives
Okay.
to immediate rewards versus future rewards.
Okay. So like short-term versus long-term thinking.
Exactly.
Yeah.
And even a small tweak to that gamma value
Yeah.
can completely change how the agent behaves.
Wow, so it's super sensitive.
It is. And it highlights just how intricate these systems are.
That's wild. So we've talked about the theory, we've talked about the algorithms, but what about the real-world applications?
Oh, that's where things get really exciting.
Okay, let's hear it.
Because we're already seeing RL pop up everywhere. From robots learning to do surgery to personalized medicine that adapts to each patient.
No way, that's amazing.
It's incredible, right? And of course, self-driving cars.
Oh, yeah. Gotta mention the self-driving cars.
That's a big one.
So it sounds like RL has the potential to completely change so many different fields.
It really does.
Yeah.
And the lectures make this point too.
Okay.
We're still a ways away from that sci-fi dream of truly general-purpose AI,
Yeah, those robots that can do it all.
right? Like, we're still figuring out things like common sense reasoning
Okay. Yeah, that's a big one.
and how to get machines to make ethical decisions.
Right. Right. Those are huge challenges.
They are. And then there's this whole other level of dealing with completely unexpected situations.
So stuff that's never even been programmed into the system.
Exactly. We haven't quite cracked that code yet.
It's like we're still in the early days of exploring this whole new world.
That's a great way to put it. We've made some incredible progress,
For sure.
but there's so much more to discover.
Totally. And I gotta say, these Stanford lectures are an awesome starting point for anyone who wants to dive deeper.
Couldn't agree more.
They really break down those core concepts, the algorithms, the challenges, and even the bigger picture implications of RL.
It's a real deep dive.
It is. Well, that wraps up our deep dive into reinforcement learning.
Yeah, thanks for having me.
It was awesome having you. We cover everything from self-learning robots to the quest for artificial general intelligence.
It's been a wild ride.
It has. If you enjoyed this episode and want to learn more about the amazing world of RL,
Definitely check out those Stanford lectures.
you won't regret it. Until next time, keep those brains buzzing, and we'll see you in the next deep dive.